How effectively can a machine learning model classify images of terrestrial arthropods? Terrestrial arthropods are the subsection of the arthropod phylum that primarily lives on land. This includes insects, arachnids, and myriapods, and it excludes crustaceans aside from woodlice. Classifying images of terrestrial arthropods with machine learning could allow for quick and accurate identification. This is important for a variety of reasons, namely identifying pests, because some insects can damage infrastructure and destroy crops, and identifying these species early on can prevent outbreaks. Harm reduction, some arthropods can be dangerously venomous, and identifying these species can prevent unnecessary harm. Research, because quickly and accurately identifying arthropod species can help to accelerate research. And environmental monitoring, arthropod populations can be an indicator of environmental health, namely pollution. Many arthropods look extremely similar, even those that aren't that closely related. This makes it difficult for both machine learning models and human taxonomists to identify exact species. Closely related species are often only separated by extremely subtle differences, meaning that a machine learning model must be complex enough to detect these features. To implement a machine learning solution to the proposed research question, a dataset must be selected. I chose to use insect images with scientific names, 122k images, found on Kaggle. This dataset contains a CSV file, including the common name, scientific name, order, family, genus, and species of each of the 2,280 included species. Additionally, there are 50 plus images for each of these species, organized in a directory by scientific name. This dataset contains a vast number of images of a large number of species, making it an excellent choice for training. The downside, however, is that some of the data is corrupt, and some aren't even image files at all. Additionally, the CSV file and directory names are encoded using CP1252, which is incompatible with Python and Google Colab. It is easily resolved when importing the CSV file, however many of the directory names experience text corruption, which proved more difficult to fix. I've chosen to use a convolutional neural network. This is an effective model for image classification and is a suitable choice for my specific data. This is because it learns the features of the insects, allowing it to better generalize regardless of the pose and position of the insect in the image. Additionally, CNNs are efficient due to the parameter sharing in convolutional layers. This allows for a more complex model to be trained in a reasonable time when using images with large dimensions. So this is the layers. The amount of layers and the parameters I chose to use were in order to provide sufficient depth and breadth while maintaining a reasonable computation time. The dropout layers are for mitigating overfitting and have been fine-tuned to a rate of 0.2, which I found to be the most beneficial effects. Additionally, there are pooling layers after each convolutional layer to reduce the spatial dimensions of the feature maps in order to improve generalizability. All of the layers use the ReLU activation function due to its high accuracy for image classification tasks. The output layer returns a probability distribution of the different classes using log softmax as expected by the chosen loss function. For the loss function, I've chosen to use cross-entropy loss. This is because it heavily penalizes confidently incorrect predictions. Additionally, it provides efficient training, allowing for more classes to be classified in a reasonable amount of time. For the optimizer, I've chosen to use AdamW with an initial learning rate of 0.001 and a weight decay of 0.0001. The relatively large number of parameters and moderate depth of the model make AdamW a good choice. Additionally, AdamW's weight decay helps to prevent overfitting caused by overrepresented classes. For the learning rate scheduler, I've chosen to use StepLR. This is a simple scheduler that reduces the learning rate by a fixed factor every X epochs. In my case, the factor is 0.316, which is applied every 2 epochs. I've collected the following data for evaluation. I collected results from 5 different subsets of the dataset, each being the n most populated classes. I collected results for n equals 2, 5, 10, 50, and 100. So for 2 classes, these are the results. For 5 classes, these are the results. For 10 classes, these are the results. For 50 classes, these are the results. And for 100 classes, these are the results. So to analyze these results, there's a clear decrease in all metrics as the size of the dataset and the number of classes increases. When predicting only 2 classes, the model performs strongly, with all metrics indicating a high level of confidence and accuracy. The performance rapidly declines as the complexity increases, with results eventually becoming completely inadequate. The closeness metrics decline as complexity increases suggest that as more classes are introduced, the model struggles to identify features commonly shared between species of similar taxonomic classification. This indicates that the model may perform better given a larger depth and breadth, as it would be able to identify more subtle features that may allow for more taxonomically accurate predictions. The closeness metric declines at a quicker rate than the accuracy, suggesting that as the problem grows in difficulty, the misclassifications tend to involve taxonomically distant species. The F1 score's higher value in the simpler problems suggests that the model is confidently predicting correct labels. The decline in this metric is due to the decline in both precision and recall, which suggests that the model is giving multiple inaccurate positive predictions, with the low recall suggesting that the correct label is often not present in these positives. The declining MCC illustrates the model's decreasing ability to balance the confusion matrix as the task complexity increased. The fact it remains positive, however, indicates that even in the very complex problems, the model is still performing better than random chance. Even at 10 classes, the MCC remains in the moderate range. The unstable training loss, especially in the simpler problems, is likely due to the lower batch size. This was necessary, however, as increasing it led to much worse overall performance. Additionally, the graphs show evidence of some level of overfitting, however not to an extreme degree. It is important to consider the complexity of these tasks, as classification problems grow in complexity rapidly as the number of classes increases. A classification problem with 100 classes is very complex and would require a substantially more advanced model to achieve high success. This is likely the key reason for the drop in metrics. However, the analysis of the results provided sufficient evidence for the usefulness of machine learning in classifying images of insects. The model remains better than random chance, even when the problem's complexity is far too great for its capabilities. Additionally, the model shows excellent performance in the binary classification task, as well as moderate performance up to the 10-class problem. This provides clear evidence that machine learning is able to accurately classify insects in simple problems and suggests that the potential for more advanced models to reach a similar level of performance in more complex problems. Other than the simplicity of the model, another factor that may have contributed to the declining metrics is the dataset. 47% of the species in the dataset come from only two orders, which is Coleoptera and Lepidoptera, while the rest of the 1,219 make up only 53%. This is a massive data imbalance, which may have contributed to the decline in metrics, as the largest orders would have dominated the training data more as the number of classes increased. One potential solution may be to address the data imbalance. Introducing synthetic data to the underrepresented classes may help to improve the generalizability of the model. Another potential solution may be to increase the depth and breadth of the model substantially, allowing for more subtle features to be recognized so that even incorrect predictions are taxonomically similar. Finally, training the separate models for order, family, genus, and species may allow for better taxonomical accuracy, allowing for efficient predictions without the need for a single, massively complex model. This would require a different dataset, however, as the data would need to be organized hierarchically, and there would need to be a much more diverse spread of species in order to provide sufficient data without the massive overhead of mass image augmentation. The data collected by my model provides sufficient evidence to answer the proposed research question. With access to more powerful hardware, more advanced techniques would be available which could massively improve the performance of more complex problems. By implementing a model with the previously proposed changes, it's highly likely that accurate predictions would be possible for a wide range of arthropods. In conclusion, my research suggests that machine learning may be highly effective in classifying images of arthropods given powerful hardware, a sufficiently advanced model, and an approach that takes the biological features of taxonomic classes into account. And these are the references from earlier.